So Muthu started talking to me about this workshop sometime last year, and he said, algorithms in the field. I said, yeah, I know, field, yeah, right, that's when you have an addition and a multiplication operator, right? And he said, no, it's nothing like that. So, we talked more over the coming months, and at the end of this, finally, I still have no idea exactly what algorithms in the field actually means. But if I'm going to come to a workshop on algorithms in the field, I feel that if I'm going to give a talk, then maybe I should say, well, here's what I think is an example of algorithms in the field. Here's my attempt to make an argument. These are something that we can actually define, sort of clearly put a box around them and say, here are some algorithms. And we think they're in some field. And at least let's have the discussion about whether this is a convincing argument or whether we want to find other examples that really do fall into this category. So I'm going to be talking about this idea of sketches that Sergey already briefly alluded to. And sketch is a very convenient word because, like algorithms in the field, it doesn't really have a precise definition. But it's generally understood to refer to data structures that are compact, randomized summaries of some larger quantity of data. So in the process of this, I was trying to find, well, when did people actually start using sketch to talk about data structures? And the earliest example I could find was actually in a paper by Andre Broder back in '97, when he introduced the concept of min-wise hashing, which I'll mention on the next slide. The exact interpretation varies, but some common properties are that you sort of have your large amount of data, you're trying to approximate some function over the whole of that data, your data structure that you're using to capture this information is ideally sublinear in the size of the input. Often you'd like it to be a linear transform of the input when you think of the input as a vector. Often you'd like it to be mergeable. Okay, Piotr already wants to heckle. So I'm even flexible and randomized. Essentially I'm saying it's a definition where you can take some, all, or none of these things and we can debate this. Certainly, so at least when I tried to put this down, I thought, well, let me at least try and make this slightly poetic. So here is my haiku to try and define sketches. They are compact summary, linear, limited independence, linear transform. Okay. So if I'm going to sort of say here's a broad set of objects, let me make this set as large as possible by retroactively claiming stuff that lots of other people have done before this term was ever invented. So I claim that things like fingerprints, that is, essentially just hash values of large objects. Think of, essentially testing equality of two very large vectors. Think of Karp-Rabin hash functions. Essentially meet what my internal definition of a sketch should be. And there are ways to tweak the way you actually build the fingerprint to make them also satisfy this linearity property. I claim that Bloom filters also count as sketches. These violate one of the properties because they're not sublinear, but the constant of proportionality is sufficiently small that they seem to entertain the networking community almost indefinitely. Min-wise hashes, I mentioned, first used this term, so I better use that. Min-wise hashes essentially allow us to keep small sort of summaries of essentially of sets or multi-sets to estimate properties of their similarity or dissimilarity. Where this term has really taken off in the last decade is in these last two bullets, these ideas of counting, which I sort of break down roughly into two types. Counting sketches which summarize something about distributions, and we'll see a few examples of those, and count distinct sketches which are really concerned with sort of viewing the input as a multi-set, but tracking properties of the underlying support sets. In particular, the basic problem there is just tracking what's the cardinality of the underlying support set of a very large multi-set. So I'm going to try and claim that these sketches are in the field. And maybe I'm right, maybe I'm wrong. I'm going to claim they're somewhat successful for a variety of reasons. Often, that they're relatively simple to actually implement, and they solve some relatively simple abstract problem sufficiently well. Possibly a third reason is that sometimes these sketches can almost seem magical on the first encounter, that you're saying, I've got this huge vector of data, and I'm going to approximate the L2 difference between two vectors, the Euclidean distance essentially between two enormous vectors, by keeping essentially a constant amount of information. That doesn't seem right, but once you understand the math behind it, you see how it's possible. At the same time, I want to sort of be somewhat critical and say, well, why aren't sketches more successful? Why hasn't this fully transitioned into whatever field we're thinking of? And I think the main obstacle is simply they're not yet mainstream. Not enough people know about them. So, take this question to apply to whatever topics you're interested in. If we claim that we're interested in doing algorithms in the field, then as well as solving technical problems, we should also be asking the question, what can we do to promote the success of our techniques in the fields where we think they're appropriate? So just to make things precise, I'm going to talk briefly about a couple of different sketches, some of the applications of those sketches, and some forward steps. So in the interests of self-interest, I'll start with the Countmin sketch, which, as well as being something that I worked on, is also something I think which is one of the simplest randomized data structures that I know of, while still doing something non-trivial and interesting. So here, it sort of captures ideas that we see come out many times within these ideas of sketching, that we're, for abstraction, let's just think of the input data as defining a vector x of very large dimension m. Then our sketch representation of this is this very compact array of size w times d, where essentially we're going to build a linear transformation of this vector. I'll describe it implicitly in terms of hash functions. But the linearity means that it becomes very flexible, especially in terms of essentially performing algebraic operations on the sketch. So, conceptually, I have my large vector. For every entry in the vector, say entry j corresponds to some value c, and again, for simplicity, I'll assume these are non-negative entries. So I have my array, I have hash functions. In each row, I have a corresponding hash function. In the first row, my entry gets mapped to some bucket in that row, and I just add on the corresponding value for entry j into that bucket. I do the same in the second row with the second hash function, and so on. So what does this get me? My basic primitive out of this is, once I've done this over the whole vector, then I can go back and essentially probe any entry of the original vector and get an approximate value of that entry. And clearly I'm going to pick up some noise, and the analysis is just going to tell me how much noise do I get in the process. So exactly what's my estimation procedure? It's pretty much the same as the update procedure. I just go, I want to know what's my estimate of the value of xj. So I say, well, let's just look at all the places where j was mapped in the original place, in the original mapping, where all those plus c's marked it. All of the mass of xj is in each of those buckets. There are collisions. Those collisions slightly upset my estimates, but on average, by not too much, through the repetition, I drive down the probability of making a bad estimate down to whatever small constant that I want. And the proof is sketched on half a slide. You can teach this in a couple of slides without any serious problem. And once you have that, then you can sort of do other things on top of that. I can say within this sketch, within this vector, where are the heavy things that I'm looking for, and it's fairly straightforward to sort of go through that, either various sort of search procedures, either directly or with additional sort of binary tree structures on top. So so far this is just one sketch which solves an abstract problem, and I'll keep this in mind, and as we come back, we'll show where abstract problems like this translate into problems that people might care about. Second sketch, just to make it clear that they're not just not just one kind of sketch. There's other kinds of things people do. So I say F0 or count distinct. The basic problem is I want to estimate the number of distinct elements in a multiset. So we do this with a hashing procedure. So our elements are initially over a universe of size m. We're then going to map them onto a universe of size m cubed. M cubed just big enough so that collisions are unlikely in this setting. And all we do is we pick some number t and keep track of the t smallest distinct hash values and corresponding elements. So some element comes along, let's set t equals 2, so we just keep track of this sort of vt of the value associated with the second smallest element for this tiny example. More items come in and we update. Something bigger comes in and we don't care. The same thing comes in and it's invariant. This is why it's doing the right thing when it comes to duplicates, because duplicates get ignored. And at the end of this, we have our, just for this sort of very simplest instantiation, we have our sort of our VT is sort of telling us this associated value of the t smallest. So if things were uniform, and in some sense this hash function is giving us some uniformity over the remap domain, then if we have sort of 2 elements over this small fraction of the domain, then you can just sort of linearly extrapolate that to estimate how many would be over the whole domain, and that's more or less what your estimation is. You just do the natural, take that fraction and remap it to estimate how many distinct elements. And then again, a little bit more effort, but fairly straightforward analysis gives you a nice relative error bound on the number of distinct elements. This translates into basically saying you can estimate up to relative error number of distinct elements in space that looks like 1 over epsilon squared. And if you're so inclined, you can really hammer away at the log factors. It's also quite fast. And so you say, well, do I really care about only counting distinct things? Well, in some cases people do. They at least for audience, you want to know how many distinct people visited my website. But more than that, you can actually take these kind of ideas and sort of generalize them a little bit and say, actually, if I keep not just the hash values but the elements associated with them, then I've got something which more or less functions like a sample of the support set of the multiset that I've seen, and you can sort of estimate any function, how many, if I've got the right information, how many people from Europe visited my website, how many people using Firefox visited my website, just by keeping essentially a very small sample. So let me try and sort of take these from algorithms which solve abstract problems into arguing that here are some things which I call applications, and then we can see to what extent are we convinced by these applications. So a first sort of medium step out of computer science is in compressed sensing. This is a problem that's been really exciting the world of electrical engineering and signal processing in the last 7 or 8 years. And the problem defined there very compactly is to say, again, you have any kind of signal which you're measuring. Traditionally, you just measure the whole signal, make digitizations of the whole signal, and then think about compressing it. But that seems wasteful. Rather, in the compressed sensing paradigm, what you want to do is design a measurement matrix where once you've designed this matrix and you have complete control over what goes in this matrix, you're then given the result of measuring some signal with this matrix, essentially the matrix vector product, and you want to recover a good approximation of the underlying signal. And within this is a sufficiently high-dimensional optimization problem. You can optimize essentially the size of the measurement matrix, the density in terms of the number of non-zeros, how long it takes you to do this recovery, probability of error, and so on. So this is why this isn't this is why there's not one paper on this problem. There's several hundred, because everyone can find somewhere in this multi-dimensional space to say that they're the best. But certainly, one immediate observation was that once you start posing this signal processing problem like this, then you realize that actually these kind of sketch techniques, these kind of counting sketch techniques, immediately start yielding compressed sensing solutions with some potentially attractive properties. The corresponding measurement matrix turns out to be very sparse and actually binary, and that can map onto some actual physical measurement properties. They also tend to be associated with very fast decoding. The weakness is that they don't get the very strongest error probabilities straight out of the box, but it's led to a whole line of work using these kind of sketching ideas in sparse recovery, in actually building systems which apply this in the context of medical imaging. And so there's a good survey on this and a small wiki page talking about this field and the connection to these kind of sketches for sparse recovery. My second application is to talk about stream data analysis. Again, Sergey sort of mentioned in his talk this sort of paradigm of streaming. So to me, it's sort of streaming is all about when your data is so big that it's not even feasible for you to think of it ever actually being manifested on disk or any storage medium. That instead you're sort of having this one-look view of data, and so it tends to be dominated by network traffic analysis, but also sort of bending the paradigm a little bit, analyzing web traffic to the very highest traffic websites need these kind of techniques to be scalable. And in fact, sketches are used in these kind of systems to analyze this, in systems at AT&T and Sprint for understanding structure within telecom and network data, and actually is part of various default data analysis reports that get generated. Likewise in Sawzall, which is a tool used very broadly at Google for working with log data. The only way you're allowed access to log data is through Sawzall, and that has cooked into it various of these sketch techniques, things like the count sketch technique of Moses, Martin, and Kevin. And these as sort of a simplified, essentially as a simplified version of MapReduce. It's on top of MapReduce, Sawzall does these analyses. And that lets you then, in a relatively high-level language, quickly specify various sort of ad hoc queries to identify, what are popular queries over the logs of a certain time or a certain location, number of distinct things you've seen, and so on. So the third application I want to talk about is sensor networks. We all know sensor networks, right? They're these networks where you scatter, hundreds of thousands, if not millions of sensors around, and they all talk to each other. And of course, sketches fit in here exactly. My only hesitation is, as far as I'm concerned, sensor networks to me are more of a fairy story, right? That we can easily tell ourselves these stories that there are millions and billions of sensors out there talking to each other, but I've never seen any. And when you actually look at what they're too small. Okay, very good. When you actually look at what have people said about how do they use sensor networks, they say, well, we have 7 or 10 sensors, and we go out and we put them very carefully. But more than that, sketches and sketch techniques make sense on first glance in this setting, because you say, well, of course, I want to do in-network processing. I have all this data. It's very expensive for me to move it around, so I want to do my sort of processing in-network. But what the scientists say is, no, we want all the data. We want to make sure we get all the data back to the base station, and then we can actually do the analysis on it. So I'm not saying this is never going to be in the field, but I was trying to make a distinction here between where I actually see things in the field right now and where I see a nice story that we can tell ourselves, but nothing actually out in the field that really justifies these stories. And so there are other applications where these sketch ideas are making some amount of impact from areas like machine learning, where sketch is sometimes also called hash kernels. And when you have something with hundreds of thousands or millions of features, you don't actually want to materialize feature vectors of that size. You'd rather actually do your learning essentially in another space, and that space is a space defined by sketches. Likewise, data mining, you're sort of looking for anomalies or outliers over data of very high dimensionality. Sketch techniques can be a very good first step in allowing you to explore that space. And then things sort of get sort of a little bit fuzzier, a little bit more speculative. There's a very nice article in the New York Times last year that picked up on some work that Michael Mitsumacher and collaborators were doing, using sketches to sort of test passwords. If your password is too popular out of this huge, impossibly high-dimensional space of passwords, then maybe you shouldn't use it. Maybe you should pick another one. Seems nice. It's sort of on the boundary between field and fiction. Then as we go on, all of these things sort of make sense. Large-scale linear algebra, cluster computations, distributed monitoring, privacy preserving, but sort of hopefully these will become real fields. Right now, they're plausible. So if I want to step back and say, to what extent do I believe that these sketches represent a story for algorithms in the field really being in the field? To what extent do I believe that we can take something like this and call it a success? Strengths are things like that they're very easy to code up and use. Actually, I'd argue sometimes it's easier to use sketches than exact algorithms. Right? If I'm dealing with the exact algorithms, then often I'm storing all the data, so I have to occasionally resize my data structure so I've got room for things, have to keep track of pointers, have to worry about other strange things going on with updates and deletions. Sketches are often very straightforward. You allocate a fixed amount of space, you update them, you're done. There is still out there, and I'm sure the theoreticians here will be horrified to hear this, still resistance to the idea of using randomization and approximation in algorithms. I think this battle is being won because the things which I claimed under my banner of sketches, like Bloomfields and hashes, are getting out there, and people aren't objecting to them, especially if they understand that the false positives can be dealt with relatively painlessly. Things like sketches are deliberately, they're designed to be small, but as a side effect that makes them cache friendly. So if they're always living in the cache, then they can be very fast. At the same time, small is a virtue, but memory and disk is so cheap. I mean, $100 and I can buy 2 terabytes, right? So if you're working on you've worked on a large data set of 500 megabytes, that doesn't cut it anymore, right? So we have to sort of overcome the fact that we've been too successful at making cheap storage hardware. But there are benefits which sort of pay off this. And again, the one place where sort of the sketches have made their inroads is on data which I'm trying to make this phrase successful. I don't think it's going to work. I'm saying my data is too big to file, right? It's too big to ever actually store on disk. And that's where people have actually made use of sketches. So at least there are implementations out there, not necessarily by professional programmers, not really, maybe some sort of rather scrappy C code which assumes that all of your data is 32-bit integers. But what you really want is if you're going to argue that your algorithms are out there in the field, then you should at least be able to say, well, they're in standard libraries. You just write, init sketch, and it happens, rather than having to dig through someone's code. I like sketches because they're very teachable. Essentially, and I think they actually work very well as an intro to probabilistic analysis, because working through these sketches, you basically work through Markov inequality, Chebyshev inequality, Chernoff bounds, the basic techniques. No one actually teaches them, at least not to undergraduates. No one writes about them in textbooks yet. So this is a quote from an online discussion board where someone said, I've got this problem, I've got all this data, I need to summarize it, I need to sort of extract these things from it. Someone responded by saying, try these sketch data structures. And the original post says, oh yeah, this sounds excellent, this sounds like the bomb. Never heard of it before.